Hey everyone, thanks for watching this video. My name is Brad Markle. I'm a climate scientist and one of the faculty on the Juneau Icefield program. I'll be leading the water isotope project this year. And since it's going to be a while before any other faculty for that project are up on the ice field with you guys, I figured I would try to give you a bit of an introduction to the project and water isotopes and what we use them for in Earth and climate research. I should say that I don't really know how to make videos, and so I think I'll put on some music here to sort of hide my shoddy editing, and I'll definitely use a bunch of pretty pictures to obscure the fact that I don't know what I'm doing. The ratios of the stable isotopes of water act as tracers for various processes within the climate system, such as changes in temperature and atmospheric circulation. We've been measuring the water isotopes of snow on the ice field for a few years now, and so I thought I'd first tell you about water isotopes in general, and then specifically about what we're doing on the water isotope project on JIRP. Right, so I guess we should make sure we're all on the same page. What is an isotope? An isotope is just an atom that has an extra neutron or two in the nucleus. For example, most of the hydrogen in the world just has a single proton in the nucleus. But some of the hydrogen in the world has that same proton plus an extra neutron. That hydrogen's a little bit heavier than the other one. Sometimes it's called deuterium. These slightly heavier isotopes of hydrogen are more rare. For example, if out of every 10,000 hydrogen atoms, only 2 of them are the heavier deuterium kind. But they are stable. That means they don't decay over time. This sets them apart from radiogenic isotopes, which are used for other purposes. So water has both hydrogen and oxygen atoms in it, obviously. It turns out oxygen also has stable isotopes. So most of the world's oxygen is oxygen-16. It has 8 protons and 8 neutrons in the nucleus. But some oxygen in the world is oxygen-18. It has 2 extra neutrons in the nucleus. And again, this slightly heavier isotope is far more rare. Again, out of 10,000 oxygen atoms in the world, only 20 of them are going to be the heavier oxygen-18 isotope. The difference in mass between the heavy and the light isotope is actually really small, right? It's only a couple of neutrons. And despite the fact that the slightly heavier isotopes are so rare, if we take a sample of water or snow or ice or something, we can actually measure the relative amount of the heavy and light isotope of both oxygen and hydrogen. So we measure these isotope ratios using laser spectroscopy. And in fact, I think we'll have an opportunity to do some of those measurements in the field this summer. We quantify water isotope ratios, the relative amount of heavy and light isotopes, in terms of delta values. And there's a bunch of details in there that we can discuss later, but the important thing to know for now is that the delta value, for example delta 18O, is proportional to this ratio of heavy to light isotopes within your sample. But it's with respect to the average value of this ratio in average ocean water. So if the delta value of your sample is negative, then your sample has less of the heavy isotope than average ocean water, and if it's very negative, then your sample has much less of the heavy isotope compared to average ocean water. Right, so why should we care about any of this? Well, to be honest, I don't really care about isotopes in particular. I'm a climate scientist. The thing I'm interested in and studying is the climate system. But it turns out that that slight extra mass that the heavier isotopes of water have cause them to behave differently compared to the more common isotopes. So as water moves through the climate system, experiencing processes like evaporation and precipitation, its delta values change. That records a lot of information about the history of water in the climate. All right, let's next talk about how and why the ratios of water isotopes change. Water exists on the Earth in 3 phases, vapor, liquid, and ice. And when water transitions between these phases, the heavier isotopes tend to find themselves in the lower energy phase. For example, when you have water evaporating out of the ocean, the heavier isotopes are going to be more reluctant to leave the liquid phase and go into the vapor. And so you'll have relatively more of the heavier isotopes stay in the liquid as opposed to in the vapor. That is, the delta value of the vapor will be less than that of the water. This process where the delta value of water changes between phases is called fractionation. All right, we're next going to talk about how this process of fractionation, as water is moving through the climate system, records information about the climate. To do that, we're going to imagine we're sort of floating out over the ocean somewhere in the mid-latitudes. There's a bunch of water evaporating out of the ocean into the atmosphere. Now that water is going to be transported towards the pole by the atmospheric circulation. In this case, we're going to think about it being transported towards Antarctica. That's just because this is the main place that I work, and I already had a bunch of slides available to steal for this. But a similar sort of picture might work reasonably well for somewhere like the Juneau ice field as well. So the main thing that this water is going to experience on its way towards Antarctica or the Juneau ice field is it's going to get very cold. It's pretty warm in the mid-latitudes over the ocean, but it's very cold over Antarctica, and it's also pretty cold over the Juneau ice field as well. It turns out that warm air holds a lot more moisture in it than cold air. This curve I'm plotting here is the saturated mixing ratio. It's quantifying how much vapor air can hold depending on that temperature profile we saw. So as our parcel of air with all this vapor in it tries to make its way towards the pole, it's going to cool a little bit, and then it's not going to be able to hold as much water vapor as it had originally. And so some of that vapor is going to condense, and it's going to fall out as precipitation and snow. This process of air cooling and the vapor in that air condensing and falling out as precipitation is something you guys all intuitively know, right? This is why clouds form. It's why we have storms. Now, this process of cooling and condensation happens all along the way of our water's journey from the mid-latitudes towards the pole. And every time the water cools, condenses, and changes phase from vapor to liquid or vapor to ice, the water fractionates. That is, the heavier isotopes of the water preferentially fall out in the precipitation first. This means that as the air cools along its journey, the delta values of the vapor in that air and of the precipitation falling out of the air get more and more negative. That is, the vapor gets more and more depleted in the heavier isotopes as they preferentially fall out as precipitation first. Alright, now let's imagine the exact same scenario, but we cool down the temperature in Antarctica just a little bit. That means our water vapor that's coming from the mid-latitudes towards the pole is going to have to cool a little bit more to get to the same place. If it's cooling a little bit more, that means it has to condense and remove a little bit more moisture, and that means there's going to be a few more chances for the water to fractionate. And that means its delta value is going to go down. By the time that water gets to the same place, it will have lost more of the heavy isotopes than it did before. And likewise, if we warmed it up a little bit in Antarctica, but held everything else the same, our parcel of air wouldn't have to cool as much, and so it wouldn't be forced to condensate and precipitate quite as much, and its delta value wouldn't get as negative. That is, it would be a little bit higher. So based on this sort of cartoonish picture, we'd expect that as temperatures go up and down in Antarctica, the delta values of the precipitation, that is the relative amount of heavy to light isotopes in the precipitation, should go up and down as well. In fact, this is exactly what we see in Antarctica. The temperatures and the delta values of precipitation are extremely well correlated. And this is really the main reason that we can use the stable water isotope ratios of snow and ice as proxies for past variability in temperatures. In places like Antarctica, it snows a lot and it's really cold, and it's so cold that snow really never melts. It just builds up in layers and layers over time until it creates these giant ice sheets. So what we can then do is dig into these ice sheets and collect snow from all these layers. This is something you guys will become very familiar with this summer. Or better yet, if it's a really deep ice sheet, we can drill into it. And this is the main type of research I do. We drill into the bottom of some of the deepest ice sheets, and we pull out ice cores, and then we can measure the stable water isotope ratios in the ice in all of these layers that built up over hundreds and thousands and hundreds of thousands of years. By measuring the water isotope ratios in those layers, we can extract information about past changes in temperature over the ice sheet. In fact, this is where our longest records of Earth's climate history, or at least temperature history, come from, is these ice cores from Antarctica. This graph you're looking at here is the main ice core I worked on for my PhD. It's from the top of the West Antarctic ice sheet, and what you're seeing here is 70,000 years of water isotope variability, that is, recording temperature variability as the snow fell over Antarctica. Right, so you might be thinking, okay, surely it's got to be more complicated than that. The water isotope value of snow falling on a glacier can't only depend on the temperature there. It's got to depend on all kinds of other stuff, like the temperature that it started at, where the water came from, what kind of pathway or storm the water took to get to the glacier. What if the water isotope values change after the snow fell? And you're absolutely right. All those things do matter. The real world is like a giant mess. It's beautiful, but it's chaotic. Now, for the timescales of thousands of years that we look at in Antarctic ice cores, those things probably don't matter all that much. But on the timescales that we experience, they could well matter a lot. And it's exactly these types of details that we can try to sort out by measuring water isotopes on the Juneau ice field. As I mentioned, we've been measuring water isotope values of snow on the Juneau ice field for several years now. What we're trying to do is understand the patterns of variability in the water isotope values of the snow, both temporally and spatially, and furthermore understand what causes that variability. If we measure the water isotope variability of the snow in one place and then move a few meters away, will we get the same value? And how about as we move kilometers across the ice field, does the water isotope values of the snow change? And if it does, can we understand that variability in terms of the temperature there, or does it depend on more complicated things like the patterns of atmospheric circulation that bring storms to the different parts of the ice field? How do the water isotope values of the snow vary over the course of the year? And how do they vary between years as the climate system varies? Once the snow falls, does the water isotope content get locked in, or does it get altered by subsequent rainstorms? How does the water isotope values of the snow vary with things like elevation and latitude and distance from the coast? To look into this stuff, we'll ski and travel all over the ice field. We'll take a lot of surface samples of snow, and of course we'll also dig a bunch of deep pits and sample the whole year's snowpack. I have a bunch of ideas for things I want to measure and investigate, but you guys will come up with your own ideas as well. We'll hopefully be able to measure some of these samples with a laser spectrometer on the ice field, and then the rest will be measured after the season at the University of Alaska by Eric Klein. And yeah, it's a really fun and certainly very JIRPy time. Right, so I think that's about it from me for now. You probably have lots of questions. I don't know that this was that helpful really, but there's lots of faculty and staff and students around for you to ask those questions to now. And I'll be up and get to meet you all soon. Thanks.